Dear students, so let us see this question. Dear students, so let us see this question. In a particular region, potential energy of a particle of mass 2 kg is given by U is equals to 3x square plus 4y square joules. Find the acceleration of the particle when it is released from a position of 1, 1. So this is the given condition. So let us see how we can solve this problem. So mass of the particle is given as 2 kg. Potential energy equation is 3x square plus 4y square joules. So here by this equation we can see potential energy is changing with respect to x and y values. So we are supposed to find out acceleration of the particle. So we know acceleration is equals to F by m. So if I can find out an equation for F, and as mass is already given, very easily I can calculate acceleration. So how can we find out force acting on this particle? So we have a relation between force and potential energy. So force is equals to negative of dou u by dou x I cap plus dou u by dou y j cap. So this is the relation. So according to this relation, if I try to solve this equation, F is equals to minus of, so this is the given equation which I have, it will become 6x I cap plus 4 2s are 8, 8y j cap. So this is the answer which I got to equation for force here. So therefore acceleration is equals to F by m. So therefore minus of 6x I cap plus 8y j cap divided by mass of the particle is 2 kg. So therefore acceleration is equals to minus 3x I cap minus 4y j cap. And he is asking to find out acceleration at this position when it is released from a position of 1, 1. So therefore at x is equals to 1, 1, if I substitute x, y is equals to 1, 1, therefore I will get a is equals to minus 3 I cap minus 4 j cap. So this is the acceleration of the particle. So if I find out the magnitude of acceleration, then I will get a is equals to square root of minus 3 whole square plus minus 4 whole square. So a is equals to square root of 9 plus 16 is equals to a is equals to root to 25 is equals to 5 meters per second square. Similarly, we can also find out the direction of this acceleration also. So equation of acceleration is this one, a is equals to minus 3 I cap minus 4 j cap. So therefore if I draw this coordinate axis, so this is plus x, this is plus y, then acceleration is present like this. So this is minus 3 and this should be equal to minus 4. So resultant of these two will be in this direction. So this is the resultant acceleration. So if I take this angle to be theta, I can calculate either this angle with respect to horizontal or with respect to vertical also. So with respect to horizontal, if I take tan theta is equals to opposite by adjacent side. Here opposite side is minus 4, adjacent side is minus 3 is equals to 4 by 3. So tan theta is equals to 44 by 3 when theta is equals to 53 degrees. Therefore theta is equals to 53 degrees with respect to negative x-axis. So that should be my answer. Dear students, so let us see this problem. So here there is a pulley block arrangement. So there is a spring here which is attached to a mass of m, and this mass of m is resting on the ground. So to other end of the string we are connecting a mass of a here. So what should be the mass of this mass a, such that if I release this one, so this should be able to lift this mass just from the ground. So what is meant by just lifting here? It means that the normal reaction between this mass and ground should become 0. So what is the minimum mass of mass A that should satisfy this condition? So this is what I am supposed to find out. So let us see how we can do this problem. So initially when this mass A is released, so this spring was in relaxed position. So there was no elongation in this spring. So therefore restoring force developed in the spring was 0 when I have just released this body. So it means that when I have just released this one, it was coming down with an acceleration of g, acceleration due to gravity itself. So as it starts coming down, its velocity will increase. So the elongation in the spring also increases. As the elongation in the spring increases, spring develops a restoring force in opposite direction, that is downwards. So here the restoring force starts increasing on this mass. So therefore velocity of this mass will continuously decrease, and after some time its velocity will become 0. It means this mass will lose some potential energy, and the amount of potential energy lost by this body A will be stored as elastic potential energy inside the spring. So that amount of elastic potential energy is possible only for an elongation of phi, and that elongation of y should be able to lift this mass m here. So therefore let us consider mass A will come to rest after covering a distance of y. So after covering a vertical distance of y, this mass A will come into rest position. So the elongation produced in this spring by that time will also be y only, because this is a single string and this is a non-movable pulley, this is a fixed pulley. Therefore elongation in the spring should be equal to y. So for this elongation, the restoring force produced should be equal to ky, and this ky should be able to lift this mass mg. We know that spring always applies a force in both the directions. On this side it is pulling this pulley downwards, and on this side it is trying to lift this mass upwards. So spring always is a double-sided force, just like tension. So ky should be equal to mg, then this mass will be just lifting from the ground here. So therefore I can say y is equals to mg divided by k. So let it be my equation number 1. Okay. Now we can try to solve this problem in two methods. Let us see the first method of solving this problem. So we assumed that this mass is coming down by a distance of y. It means this mass A is losing some potential energy. So potential energy lost by this body will be stored as elastic potential energy inside the spring. So therefore I can say m a g y, this will be the potential energy lost by body A. This should be equal to half ky squared, the elastic potential energy stored in the spring. So we can cancel these two. So therefore ma into g is equals to half into k into y. Y value we have calculated, which is equals to mg divided by k here. So k and k gets cancelled, g and g gets cancelled. So therefore I got ma is equals to m divided by 2. So the mass of A should be equal to half of the mass of mass m, which is present on the ground. So same problem, let us see how we can solve by second method. So here I can use work-energy theorem. Let us try to use work-energy theorem in this condition. So what is work-energy theorem? We know that work done due to spring plus work done due to gravity should be equal to delta K, change in kinetic energy of the total system. So in this condition, spring is doing negative work here because elongation will be in one direction, but spring develops restoring force in opposite direction because spring is elongated from the mean position. So work done by the spring will be equals to half k y square for an elongation of y. And work done due to gravity, and gravitational force will do work on this mass because this mass will come down by a distance of y here. So gravitational force is acting downwards, this body also comes down, so therefore work done by gravity will be positive. That I can write it as mg into y should be equal to delta k, k final minus k initial. So previously all the bodies, they were in rest position, so initial kinetic energy was 0, and finally also after coming to a distance of y, then also the body will stop, so therefore its final kinetic energy also will be 0. So therefore again we got the same equation here. So this is ma, mass of A. So therefore ma gy is equals to half k y square. So y gets cancelled, so again I got the same relation if I compare here. So therefore I can write again ma is equals to m divided by 2. This should be my equation. Let us see how we can do the same problem by using a third method also. So here we can use the law of conservation of mechanical energy. So what is law of conservation of mechanical energy? K initial plus U initial is equals to K final plus U final. Initial kinetic energy plus initial potential energy must be equal to total final kinetic energy plus final potential energy. Just we have discussed that initial kinetic energy is 0. So initial potential energy is existing only for this mass. If I take this as my 0 potential energy position, where this mass will finally reach to a displacement of y. So therefore when compared to this point, this body has lost some potential energy of how much? Initially it has some potential energy of mg divided by y here. So final kinetic energy is also 0, and initial what you call final potential energy stored in the spring will be half k y square. So therefore this is ma. So ma gy is equals to half k y square. So y and square gets cancelled, so again I got the same relation, ma into g is equals to half into k into y. So therefore ma into g is equals to half into k into, instead of y I can substitute mg divided by k. So k gets cancelled, g gets cancelled, so ma is equals to m by 2. So these are the three methods in which I can solve this problem. See here, in this third method, we need not consider the potential energy of this mass m, because initially also with reference to this line it has some negative potential energy, and finally also with reference to the same reference line, this mass has same amount of potential energy. So initial potential energy of mass m and final potential energy of mass m, they are both one and the same, so they get cancelled. So we need not consider the potential energy of this mass m initially and finally. Dear students, so let us see the next question here. So this is the given arrangement which is present in this condition. So if this mass, if it is released from rest, we are holding this one and we are releasing this one, then we are supposed to find out what is the maximum elongation in the spring and also what is the elongation at the mean position. This we are supposed to find out. So initially when I release this mass, then what will happen? So this mass may come down by a distance, and then we are supposed to find out what will be the elongation in the spring. For example, if I suppose if elongation in the spring is y, it means that this spring is attached to this pulley. So this pulley will come down by a distance of y. So if pulley comes down by a distance of y, then it will release y length from this side and y length from the other side also. So this mass will come totally down by a distance of 2y. So this is a constraint relation which we must derive to solve this problem. So this also we can derive by using the virtual work method also. So summation of t into x should be equal to 0. So therefore here if tension is T, here if tension is T, so same string, so definitely tension will be same, and the tension developed in the spring will be 2T here. So spring, this 2T is pulling this spring downwards, and spring is coming down by a distance of y. So therefore we can write 2T into y, and here on this mass tension is acting upwards but body is coming down by a distance of y dash. So therefore I will write minus t into y dash should be equal to 0. So t gets cancelled, so y dash is equals to 2y. So in this method also I can calculate. So y is the distance, the elongation produced in the spring, and y dash is the distance this mass m will come down. So we got the first relation here. Now if I release this mass will continue to fall down. Initially it will have an acceleration of g because spring was in a relaxed position. So after it starts going down, so what happens is the spring starts elongation, so therefore restoring force starts pulling this mass upwards. So its velocity continuously becomes 0, and after traveling a particular distance of 2y, its velocity will become 0. It means this body has lost some potential energy, and the same amount of potential energy lost by the body will be stored in the form of elastic potential energy of the spring. So therefore how can I solve? I can solve the energy lost by this body will be equal to m into g into distance it has fallen down is 2y. So this should be equal to the energy stored in the spring, which is equals to half into k into, and elongation produced in this spring is, whose spring constant is k, the elastic potential energy stored will be equal to half k y square. So this y and square gets cancelled. So therefore I can write y is equals to 2 into 2 4 mg divided by k. So in this method I can solve this problem. So same problem I can also solve by using either virtual work method, or also I can solve by using law of conservation of mechanical energy also. So let us try to solve in one more method, second method. So here I will try to use work-energy theorem. So here two forces are doing the work. One is work due to gravitational force, and another force which is doing work is force due to spring also, it is doing the work. So therefore work done due to gravity plus work done due to spring, totally it should be equal to delta k, and we know that change in kinetic energy of all the bodies is equal to 0. So work done due to gravitational force on this body will be m into g into 2y plus work done due to spring. So spring is elongating downwards, so restoring force will develop in opposite direction. So work done due to spring will be negative. So minus a half ky square is equals to 0. So therefore again we got the same relation. So mg into 2y is equals to half k y square. So y and square gets cancelled. So therefore I can write y is result. So therefore y is equals to 4 mg divided by k. So this is how we can use the work-energy theorem. Now we are supposed to find out what is the elongation at mean position also. So this elongation, this is definitely, it is not the mean position. So it is that position where total potential energy up to certain level of this body is converted into potential energy of the spring. So when this body has come down by a displacement of 2y, then there will be a net force which will be acting on this body. So there will be definitely acceleration present on this mass m. But at the main position, this mass will be at equilibrium. It means the upward forces and downward forces will be equal. So now if we consider the equilibrium position, then for the equilibrium position, this mass will have two forces. One is tension, another one is mg. So at equilibrium position, definitely I can say T must be equal to mg in this condition. So on this mass, if tension acting is T, then in the spring tension acting will be 2T, because this is the spring, this is the pulley, and this is T, and this is also T. So therefore here tension acting should be equal to 2T. And this 2T is responsible for elongation of the spring at the main position. So therefore I can write 2T should be equal to Ky dash. And y dash is the elongation in the spring. So 2 into, instead of T I can write mg is equals to Ky dash. So therefore y dash is equals to 2 mg divided by k. So this is our answer. So now if you compare these answers, maximum elongation is 4 mg divided by k, but at the what you called equilibrium position, y dash is equals to 2 mg divided by k. Dear students, so let us see the next problem. So two blocks M1 and M2 are connected by a non-deformed spring resting on a rough ground. So this ground is rough here. So coefficient of friction is mu. So find the minimum force F to be applied on M2 so that M1 just starts sliding. So what is the minimum force I have to apply here such that this M1 is ready to slide? So that is our question. So if I start applying force on this mass M2, then what happens? Initially only force F is acting on M2. So if I start pulling this M2, restoring force starts developing inside this spring. So after covering a distance of x, the restoring force developed in the spring will be Kx, and that Kx also gives a force on this mass M1 also. And this Kx, if it is equals to the limiting friction present between this M1 and this ground, then M1 is ready to slide. And when the applied force and Kx, they must be equal, because the force which I am required to find out will be the minimum force which I am supposed to find out. So therefore let M2 moves by a distance of x. So therefore spring elongates by, spring also elongates by x. Therefore restoring force in the spring should be equal to Kx, and this restoring force will be acting on both sides, because we know that spring applies equal amount of force on both sides also. So here also a force of Kx is applied, here also a force of Kx is applied, and this Kx should be equal to the limiting friction which is acting on mass M1. So limiting friction we know it is equals to mu into n. So in this condition it is mu into M1 into G. So up to here we got the relation. Now let us see how we can use the work-energy theorem. So from this I can also calculate x value. So x is equals to mu m1g divided by k. So let it be my equation number 1. So now we will use the work-energy theorem. So let us see how many forces are doing work initially. So applied force, this is the external force, this is also doing some work. Friction is doing some work, and spring is also doing some work here. So therefore I can write work done due to external force, work done due to friction, plus work done due to spring. So totally it should be equal to change in kinetic energy. And change in kinetic energy is 0 in this condition because initially mass m2 was in rest position, and after traveling to a distance of x, so applied force and kx, they are becoming equal because we are studying about minimum force required. So final kinetic energy also should become 0. So therefore external force is applied in the one direction, displacement is also in the same direction. So work done due to external force will be positive. So therefore I can write F into x. And work done due to friction will be negative because m2 moves in one direction, friction acts in one direction, other direction. So minus of mu m2g into distance moved by m2 is x. And work done due to spring is also negative because spring is elongated from the mean position. And if spring elongates from the mean position, we know that spring does negative work because elongation will be in one direction, restoring force will be in exactly opposite direction. So minus a half k x square, totally it should be equal to 0. So this is the relation up to which I got. So I can write this x and square gets cancelled. So therefore I got F is equals to mu m2g plus half into k into x. Now if I substitute x value in this relation from equation number 1, so let it be my equation number 2. So F is equals to mu m2g plus half into k into x value is mu m1g divided by k. So k gets cancelled. So F is equals to, here I can take mu g as common. So m2 plus half of m1, that's all. So this should be my answer. See this next question. So here this is two blocks of same mass m and m. They are connected by a spring, and initially this system is in rest position. We are not applying any forces and system is relaxed here. But we know that because of this mass, this spring will be compressed by a small value. That is a different condition. So now the question is, what is the minimum initial compression such that when force is removed, lower block just lifts off from the ground? That is the question. So by applying some force, I am compressing this spring from the relaxed position, and that is when forces are in equilibrium. And if I remove this force, we know that this block M tends to move upwards, and spring again it will tend to elongate. Then the elongation produced in the spring will produce restoring force in the spring, and that restoring force should be able to just lift this mass upwards. So that is the normal reaction present between this lower mass and the ground should be equal to 0. Then what is the minimum force I have to, minimum compression we have to give? That is the question. So let us see how we can understand this question. So first let us try to draw the minimum, the condition when forces are not applied. Then this is mass m, this is the spring, and this is another mass m, and this is my mean position. Now I have applied some force, and this is the same mass m, but spring now it is compressed, and this is another mass m, and let initial compression be x, and by applying a force of F in this condition. Now when I remove this force, first body will go to the mean position. First of all it will go a distance of x, and from there, because after going to the main position, velocity of this block will become maximum. So because of that inertia, it will go to another extreme position. So now we can draw that situation also. So this block may reach up to here. So this is the next condition. So this is m. So from the mean position, it has gone to a distance of y now. So these are the conditions. So this velocity after traveling to a distance of y from the mean position, its final velocity has become 0. And when this final velocity has become 0, the elongation produced in the spring is also y from the main position. So therefore the restoring force produced in the spring should be ky, and this ky should be exactly equal to the weight of this body mg. So therefore y is equals to mg divided by k. So after reaching y, if velocity of this body has not become 0, it will go another by further distance. Then restoring force developed in the spring will be again more than ky, and that will not be the minimum compression which is required. So therefore after reaching to a distance of y, velocity of this mass should become 0, then only the compression required for lifting this body will be minimum. So this is my equation number 1. So y is equals to mg divided by k. So now we can use again the work-energy theorem to calculate what is the initial compression produced that we have to compress this spring. So we are using work-energy theorem. So how many forces are doing work in this condition? So gravitational force is doing work, spring is doing work. So these are the two forces which are doing work, and total change in kinetic energy is 0. Because when we have applied this force, this mass and this mass were in rest position. Then after traveling to a distance from the mean position of y also, this mass is in rest position, because we are studying about the concept of minimum compression. So therefore gravitational force has done how much work? First of all, gravitational force has done work on which body? Gravitational force has done work only on upper body, because this is the only body which is moving upwards. And now what is the total distance traveled by this mass? Initially, to go to the mean position, it has to cover a distance of x. Then from the mean position, again it has to go a distance of y. And also work done by gravity in this condition is negative, because gravitational force will be acting in downwards direction, but the mass is moving upwards. So therefore minus mg into x plus y. And work done by the spring here. So spring initially it was in compressed position. So from the compressed position, first of all there will be a relaxation of m here, relaxation of x in this condition. So here spring will do positive work, because restoring force will be in this direction, and elongation is also, that is relaxation is also in the same direction. So therefore half k x square. So this is the work done by the spring up to the mean position, and from the mean position again it is being elongated to a distance of y, and from here onwards spring starts doing negative work, because from the mean position restoring force start acting in downwards direction, but elongation is in upwards direction. So minus half k y square, totally it should be equal to 0. So after this, now we know mg is equals to ky, and also y is equals to mg divided by k. So if I substitute these values here, let us see what is the result we will get. So therefore the result which I will get is minus ky into x minus ky square, and plus half kx square and minus half ky square. Totally it should be equal to 0. So k and k are present, so all k values they get cancelled. So k and k gets cancelled. So what is the equation I am getting? The equation which I am getting is this x square minus and 2, and if I multiply total by 2, then what I will get? I will get 2xy minus 3y square. It should be equal to 0. So if I observe here, I got a quadratic expression here. So this quadratic expression can be solved by using the relation of minus b is equals to minus b plus or minus square root of b square minus 4ac divided by 2a. So if I solve this expression, then the result which we will get is x is equals to 2y plus square root of 4y square plus 12y square divided by 2. So 16y square, so it will be 4y plus 2y will be equal to 6y by 2 is equal to 3y. So x is equal to 3y. So 3 into y value already here we got, which is equals to mg divided by k. So x is equals to 3 mg divided by k. This should be our answer for initial compression, such that after traveling to a distance of y, the restoring force produced in the spring should be able to just lift this mass upwards. So dear students, so let us see this problem. So here a spring is connected by two blocks, 2 kg and 2 kg, A and B. So they are connected by a spring whose spring constant is 1000 Newton per meter. So, and these blocks, they are placed on a rough surface having coefficient of friction 0.5. So I have to compress this body B such that if I release this one, then this 2 kg body should be just, it should leave contact with this vertical wall. That is the question. So what is the minimum initial compression so that block A just loses contact with the vertical wall? So this condition is exactly almost equal to the previous condition of vertical spring, which was compressed and released such that the block which was at the bottom, it loses contact with the ground. So here also same condition. So therefore let us say that let initial compression in the spring is equal to x. So after compressing by a distance of x, and now if I remove the deforming force, so this block B, first it will go to the mean position, then it starts going to another extreme position because its velocity has not become 0. After coming to the mean position, actually its velocity become maximum. So because of that inertia, it starts moving to another extreme position. And now let us say block B has further moved by a distance of y. So therefore, the elongation in the spring should be equal to y. So this elongation will produce a restoring force in the spring y, and this restoring force should be able to overcome the limiting friction present between 2 kg block and this ground. So therefore the restoring force produced in the spring is ky, and this ky should be equals to mu into n. So this is equals to mu into m into g. So mu value is 0.5, mass is 2, g value is 10. So therefore from this I can calculate y value. So y is equals to 0.5 into 2 into 10 divided by k. So 0.5 into 2 into 10 divided by k value is 1000. So 0 gets cancelled. So therefore 0.02 into 0.05, 0.5 is equals to 0.01 meters. So this will be the elongation in the spring for which 2 kg body loses contact with the ground because it has friction has reached to limiting friction. So now let us see how we can use work-energy theorem in this condition. So how many forces are doing work in this condition? Let us see those forces. So one force is friction, which is doing work. Another force is work is done by spring also. So therefore I will write, so work done due to friction plus work done due to spring should be equal to change in kinetic energy K final minus K initial. So K initial is 0 because it was in compressed position, and K final also must be 0. So after traveling a displacement of phi, this body B should stop. Then only the elongation produced in the spring will give restoring force, and that restoring force is enough to pull this block 2 kg. So after traveling a distance of 2y, y also, if body has some velocity, then definitely that is not the minimum compression which is required. So after traveling a distance of y, this block should stop. So therefore its final velocity also should be equal to 0. Now friction is doing work on which body? Friction is doing work on only block B. And block B has totally traveled a distance of x and y also. X up to mean position, and from the mean position again it has traveled a distance of y, and friction always does negative work in this condition. So therefore I can write, so minus mu into n into x plus y. So minus work done due to spring, and spring here it will do two works. So when it is in compressed position, to come to the mean position it will do positive work. So that is half kx square, and from mean position it again elongates by y, so there it will do negative work. So I hope you can understand why it is positive and negative, because already we have discussed these things in the previous conditions. So totally it should be equal to 0. So therefore, so minus mu into, here normal reaction is nothing but m into g into x plus y plus half kx square minus half ky square. Totally it should be equal to 0. So if I substitute all the values which are present here, y value already we have calculated, it is 0.01, and k value it is already given as 1000. If I substitute these values, then the equation which I should get is 500 x square minus 10x minus 0.1 minus 500 into 10 power minus 4. Totally it should be equal to 0. So now if I see this relation, this is a quadratic expression, and I can find the roots by using x is equals to minus b plus or minus square root of b square minus 4ac divided by 2a. So therefore I can calculate, if I substitute all the values, then I can calculate x value. So x value will be 10 plus or minus square root of 100 plus 300 divided by 1000. So I hope you can do this calculation. Then x is equals to, here it is 300 plus 100, 400, 200, square root of 400 is 20. So 10 plus or minus 20 divided by 1000. And now considering only positive value, then I will get its value should be equal to 0.03 meters. That should be our initial compression, so that 2 kg body leaves contact with the vertical wall.